Okay, let's take a look at problem number 3. Go ahead and read it, do part A on your own, then come back to the video. Okay, so hopefully you recognize this is a very similar situation to our previous problem. Both problems 2 and 3 are motion along a flat horizontal circle. Once again, before we draw the free body diagram, it's a good idea to put some information off to the side, but again, because we're looking at it from the side here, this car is coming directly towards us, right? So drawing the velocity vector is not a good idea. So hopefully if you picked it up from last time, or if you didn't, well, don't do the velocity vector. So if you drew anything for the velocity, get rid of it now. It's only going to confuse you. There are ways to draw the velocity vector coming directly towards you, but we're not going to do that. Okay, but the acceleration net force you definitely should have been able to draw because it's moving in a circle, and the centripetal acceleration, centripetal force, always point towards the center. So where's the center? Well, you can't see the whole circle. The rest of the circle is somewhere out here, so the center is somewhere over here. So hopefully you drew the centripetal acceleration and the net force pointing to the right, inwards towards the center of the circle. And in terms of the free body diagram, what do you put on here? Well, of course, you're going to draw weight and normal force. It's on a flat circle. There's nothing happening vertically, so normal force just matches the weight, so draw it the same length as the weight. But obviously, we're missing something, right? How do we know we're missing something? Well, just like in problem 2, the net force has to point to the center, to the right, and right now, nothing is pointing to the right. This is a huge clue that you're not done with your free body diagram. Something has to point to the right. What could it possibly be? Well, since this is very similar to problem 2, hopefully you recognize it's going to be the friction force, the static friction force, just like before. And so pretty much, if we have an object moving in a flat horizontal circle, we need something pointing to the center. Very often it is a friction force between the surfaces, the grip of the tires in the road, preventing the car from sliding on the road. Okay, if that's all good, go ahead and do parts B, C, and D on your own. Pause the video as you do, then come back. Okay, so for B, hopefully your gut tells you the right answer, but if not, there's always the equation. If we're looking for whether we need more or less force depending on speed, well, we're talking about force. We're talking about, in this case, the friction force, because obviously the weight and normal force have nothing to do with the net force. They're not even pointing the same dimension, and they're going to cancel each other anyway. We're talking about the friction force, which is the net force, and net force in circular motion is also called centripetal force. And our equation for centripetal force is mv squared over r. So clearly, with everything else staying the same, the mass of the car, the radius of the circle staying the same, more speed necessitates more force. So we definitely need more force to make that happen. All right, so now for letter C, we want to find the maximum speed can be going, and here we're given the coefficient of static friction. So remember, just like last time, this is a static friction force. So we can say that sigma F equals mv squared over r, or if you've done sigma F equals mac, that's great, but we need to get the speed into this, so we need to replace a sub c with v squared over r. And the net force, the centripetal force, is provided by the friction force. So in this case, we just substitute in friction force equals mv squared over r. And at this point, you could rearrange and solve for v if you'd like to, but let's see if we can keep going with the equation, see if we can simplify it further. Since we're talking about the maximum speed, that means the friction force is maxed out, and so we can replace the friction force with the equality equal to mu sub s times n. And at this point, if you want to solve for v, that's great. But let's play around just a little bit more with the algebra, because what do we know about normal force? Oh, right, normal force is balancing out the weight, so they're equivalent to each other, so we can replace n with mg. Why did I do all that? Well, let's see what happens, right? What can you do to simplify? We're always looking to try to make it as simple as possible. And so, again, you can see the mass drops out. And so, if you've been following along with this method of solving, at this point, definitely do pause the video and solve it for v. Algebraically, right? We always do the algebra first. Always, always, always do the algebra first. I hope you've been doing that all along, right? That's the way I've been training you. And so we should get this, the square root of mu sub s times rg. Is this a new equation? No, not at all. This is just for this particular situation. And it was about 1, 2, 3, 4, 5 steps or so to get there. Nothing was too difficult. This is all just putting together other equations. So at this point, you can go ahead and substitute numbers in. And you should be getting 16 meters per second. Now, alternatively, if you did calculate a couple other things along the way, let's say you just calculated the force of friction by doing mu sub s times n, where n is equal to mg, and you got the force of friction was equal to 3,600 newtons, then you would have gotten the speed as 15 meters per second. I think we can all agree 15, 16 meters per second. We're only dealing with 2 sig figs in the problem, but they're the same thing. And I hope you are only doing 2 sig figs, because the coefficient of static friction has 2 sig figs in it, so we're limited to 2 sig figs in our answer. All right, so how about for letter D? Now, it's on the same car, it's the same car traveling the same track, but all we do is we change the tangential speed. How much friction? Well, even though it is a static friction, which can have an inequality, has a whole range of values, well, the force of friction is mv squared of r. So we're just going to find a different force of friction. That, the 3,600 newtons is the maximum it could possibly be. We're just finding a different number. And so we'll just put the numbers into this equation, and you should be getting 1,500 newtons. Clearly smaller than the original, which makes sense. This goes right back to part B, that if it's moving faster, we need more force. Obviously, if it's moving slower, we don't need as much force. That should make perfect sense.